All right. Thanks, Andres. How are we on the sound? We're good. Okay. Thanks, Andres, for inviting me for the gluten-free pizza. Thank you for the organizers. So the title here, Rediscovering Reactive by Applying Duality. This subtitle, Lost Art of Denotational Semantics, was mainly to scare everyone away so I could have all the pizza to myself. But you guys are brave. You came. I appreciate that. Actually, it's same title of a talk by Erik Meijer. And I've watched several talks by Erik Meijer. He is a programming language architect that I really enjoy watching. We'll talk a little bit about him later. So it's just to remind, basically I'm trying to rehash that talk sort of in my own words. So what we're going to be looking at is duality, and the point of duality is look at things from two sides. Take advantage of the light side and the dark side. Don't let Star Wars fool you. Both sides are good. And you want to take advantage of both of them, and that's exactly what Erik Meijer does. There's some talks you can find that I'll link later that he uses duality to actually discover the .NET Reactive framework. And we're basically going to go through that process. I'll talk about why we'd want to do that, who Erik Meijer is. I need to define this term, denotational semantics. Since I put it in my talk, I should at least define it. Then a warm-up example, but it's actually going to be most of the talk, is product types and sum types. These are two duals, which I think actually come up the most often in everyday programming, so I think it's a good case to understand, and like a warm-up for the dualization we'll do later. Then finally, I'm going to cover basically a short summary of what Erik Meijer covers when he talks about dualizing iterable and iterator to get observable and observer. Okay, anyone know who this is? Either one. Yeah, everybody knows Weird Al. That's the guy on, I guess it's also your left. The guy on the right is Rich Hickey. He basically designed Closure. It's a Lisp on the JVM. And I guess Weird Al was his inspiration. But he has a talk called Simple Made Easy. Really good talk. I highly recommend it. Doesn't really relate to anything in this talk except that simple and easy are not the same. So I just want to say that we're going to dive into some like mathematical type stuff that's actually simpler, but maybe not easier. And what I mean by that is that I'm not really worried about, when we talk about the code that we're looking at, I'm not worried about things like cache misses, memory layouts, memory limits, garbage collection, performance, security, versioning, building, class loaders, deployment. Those are all things that you have in your programs that you write every day that are extremely difficult to get right, and you get them right every day. What I'm actually doing is denotational semantics is actually a way to simplify a look at your programming language or your code to see what it does. That ignores a lot of these complexities. But I'm not going to say it's like easy. So the sort of dual to that is a presentation on using a framework. Frameworks are by no means simple. There's all kinds of things you have to set up, but they can be easy in that you can copy and paste some code and get some things up and going. So that's kind of I'm going to try to do a high-level view, simple but not easy, and that's sort of the motivation I'm getting from there. So what we're going to talk about, the simplification, is basically I want to ask the right questions. That's kind of the overall picture. And what we want to look at is reactive observable. There's a link to the Java doc there. I will have a link to these slides. It'll be on my LinkedIn page, but I don't know if I can put it on the meetup or something. I'll figure that out later. But if you look at the observable class Java doc, it's actually enormous. So I'm going to simplify incredibly. I'm going to look at one method from that class called subscribe. That subscribe takes an observer, returns a subscription. I'm not going to talk about what subscription is. That's simple. But an observer has 3 methods in it: on, next, on error, on complete. So when I say reactive framework, that's really all I'm talking about is these 2 classes and these method signatures. Like, I'm not talking about actually the details of how to use them and combinators that you can use on them and all that stuff. So that's the first part at which we're simplifying. Okay, so Erik Meijer, who is this guy? He's looks like this. If you see a guy wearing tie-dye these days, it's probably Erik Meijer. He's a pretty entertaining speaker. He's a bit crass, cusses a lot in his talks. He's irreverent, so just fair warning if you're going to watch some of his talks at work or something. He has a PhD from the Netherlands. I'm not going to try to pronounce that. Worked at Microsoft from 2000 to 2013. The big notables are Link and .NET, or RX.NET. He's, I think responsible for both of those. You know, had a team that helped design and all that stuff, but he's sort of the brain behind it all. He's one of the world's leading programming language designers. After that, he left, started a company called Applied Duality. That's the logo there. And now I think he works at Facebook doing some machine learning to help autocorrect code or make suggestions for error correcting and stuff like that. I'm not going to go over all these links. I'll share the slides and you can look at these. These are just some of the videos and articles that inspired me. And it includes the last one there is The Lost Art of Denotational Semantics, the one that mainly inspired this talk. Okay, so I have to give a definition of this fancy word from Wikipedia. It's an approach of formalizing meanings of programming language where you construct mathematical objects. Those mathematical objects are just called denotations. Semantics is a word for meaning of programming language. So it's meaning by assigning mathematical objects to the expressions. So why do we do this? And the reason is for precision. There's often stories like this. A business user says, hey, developer, I need you to run the store, pick up a loaf of bread. If they have eggs, get a dozen. Developer completes the story quickly, says, I got a dozen loaves of bread. Please test, right? So this is the motivation Erik Meijer gives for doing denotational semantics is it gives you a language which is more precise to speak about things. And it's precise while at the same time simplifies. And I think that's pretty powerful. And the reason it does that is because it's basically based on mathematics. And mathematics is not like a framework that Oracle or Sun or Eclipse Foundation came up with. Mathematics is, lasts a lot longer than that. So if you can write something which has a foundation on mathematics, your likelihood that you'll have written something that stands the test of time is much higher. Okay, so we're going to be talking about duality. Just to get your mind wrapped around duality, all I mean is things that are dual. Addition and multiplication are dual. I'm not going to talk about exactly how they're dual yet. We'll get into that later, but just to think of examples of things that are dual. And is dual to or. Minimum and maximum are dual. Union, intersection, dual. There's a Venn diagram there with some intersections and unions. SQL and NoSQL, actually. There's an article by Erik Meijer linked in the previous one that talks about, he prefers to call NoSQL co-SQL. Co is sort of the mathematical term for dualizing something. And so he shows that SQL is just flipping all the arrows around, which is dualizing. Splitterator and collector are actually dual in a way. That's a talk I'd like to give in the future. We're going to talk here about products and sums, iterable and observable being dual. Okay, so first time I gave this talk, I think I gave into the mathematician's sort of overly abstract nonsense way of looking at the world. So I'm going to try to be a little more concrete. Please feel free to ask questions if I sort of drift into abstract nonsense. But so this is an example, a really simplified example of a problem we actually had at PCI. We had to write some code that said balance transmission and generation. Okay, so Reasoning is I have some transmission lines, I have some generators putting power on those transmission lines. The transmission that I schedule on the lines has to equal the generation that I schedule to balance the system out. So this method is a consumer of a transmission object and a generation object. So I'm highlighting consumer and because those are the things that we'll dualize later. So first we'll dualize consumer to producer. So the question is, what method signature produces a transmission object and a generation object? Basically, what's upstream of this thing? What computed the transmission and generation that I'm now going to balance? So this is where we get into this product type. So if I want something that computes, one thing that computes a transmission and generation, basically I define a new class, right? I'm going to call it balance input, because I can't think of a better name, and it has two fields, transmission and generation, and I'm leaving off equals, hash code, getters, all that stuff, so it's readable on the slide. Okay, so now I have a method signature that computes this thing. It's balance input, compute transmission and generation. That's upstream, and then downstream, instead of that balance transmission and generation, it's now balance the input, and that is a transmission and generation. All right, so semantically, those are clearly the same. And so one thing I want to note is what I've done here is just use the composite pattern from the Gang of Four design patterns book. That's kind of a theme of this sort of math and programming language. There are some talks out there about it, and in a lot of them you'll find that you'll rediscover patterns that are in that book as some kind of mathematical object, and we'll see a couple of those here. Okay, so what I want to get across is the semantics of this product type, and I'll explain the term product type in a second, is basically and. Basically, I have a transmission object and a generator object. So in fact, I could have used the Apache pair class, which is a generic and basically. I could have used pair, transmission, and generator. I could have used map.entry. Pair actually implements map.entry. That's an interface. Or I could have used balance input. And I put the arrows here to mean I could construct one from the other, and I can go all the way around the circle, and once I'm done, I can't tell the difference between the two. So what I mean here is that when I talk about product types, I'm not talking about a particular construction. I'm just talking about the denotation, the mathematical meaning, is just, all of these have the same denotation. That's what I mean. Even though there's a bunch of complexities in terms of why I would use one or the other, when I'm talking about the denotational semantics here, I'm simplifying all that. I'm not worrying about hash code, I'm not worrying about the dependency, the exact version I need, what the constructor is, what the serialization, all of that stuff. Or which one's more user-friendly. So I'm just thinking about this is a transmission type and a generator type. That's what I want to emphasize is the simplicity. So let me explain where the term product comes from in product type. It's actually super simple. All you do is count, right? But it only makes sense if you have finite something you can actually count, right? So pair, Boolean. Let's ignore nulls for now. How many pairs Boolean I can have? Well, I can have all the true false pairs. So there's 4 of those, right? Pair Boolean and this enum that I put up here with 5 elements. Well, I can have 2 types of Boolean, 5 types of log level. I combine those together, I have a total of 10. And in general, here's my mathematical notation. The size of the pair is the product of the sizes of the 2 types. That's why it's called product type. So fairly straightforward. And of course, this is true whether I would have used pair or whether I used map.entry or whether I would have used balance input, whatever. Okay, so this is the hardest slide, maybe the equal to the hardest slide in the whole talk. So if you want to tune out at this point, feel free. I just want to give at least some formality to this, and if this is sort of too much, then don't worry about it. But basically, the idea is I have two objects, T and G, that's transmission and generation, two types, two Java classes. The product P is a solution to this problem. Basically, if I have two computations, given any type X, I have a way to compute T from X. So that's this arrow. If you look at this X arrow T and X arrow G, I have two computations. One can compute a T, one can compute a G, both from X, right? Well, I can replace that computation by a single computation which just computes P from X. And if I want to recover the individual T and G, I can just get left or get right on the pair, right? Or whatever implementation I have, balance input, I can say get generation, get transmission. So the point is, this construction is just a way of taking two types and a relationship of those types to the external world. This relationship is just, they're the product of a computation from one thing, and replacing it with one type, right? So that's very mathematical, and I'll show you why. If I do the exact same construction, and now I have numbers. So now I say, given a number such that instead of you can compute T from X, I say T is less than or equal to X. So I have the exact same structure of my problem, but I've replaced computation by less than or equal to, and I've replaced types by numbers. What you get is maximum. So in that way, the pair construction is just like the maximum construction, which is just a way to take two numbers and get another number, right? So pair is a way to take two product type, is a way to take two types and get another type. So that's, I want to emphasize that this kind of construction is deeper than just programming languages. It goes, you can do this across a wide range of contexts and get interesting results. And it basically says that there's something deeper going on here than just, some programming language construct. That's what I want to get across. And that's what Meijer emphasizes. That's why he likes to focus on sort of mathematical types when he thinks about programming languages, is because you get sort of this depth of reasoning. You basically get, mathematics kind of tells you what are the interesting questions to ask in a way. I have several more examples here. You can do least common multiple as another example. You can look at these on the slides. I'm not going to go through them all. But basically, if I take this exact same template and I replace the context that I'm working in, I get a construction that you know about. So the intersection construction is the exact same way. So intersection and product, intersection of sets, product of types, they're the same construction in two different contexts. All right, that was the hardest chunk of the whole thing. So I don't know if I've lost anyone. Please ask questions. But okay, back to the example. I'm going to try to start doing the dual of this product type now. This is a little harder to motivate because the Java programming language doesn't support the dual of product really out of the box. It's kind of awkward. But it'll turn into another pattern, we'll see. It just has a lot of boilerplate. So let's go back to this example. I have balance input, which is my transmission and generation, and I have a balance result, and I haven't said anything about what balance result is. So I'm looking at a producer. Now I'm going to tell you the balance result, there's two types of results. I could have a balance delta or a limit violation. So what I mean is, in the business context here, I could say, all right, I need to move the transmission and the generation by all these deltas, and that's how I balance. Or I could say, I need to move them, but I'm going to violate this line can't take this much generation, or this generator can't move up that much or move down that much. So I actually have some sort of attempted balance result, but some violation of some limits. It's a different kind of result. So downstream of this, you would have two different methods to consume those different kinds of results. So now I have a consumer of the result and the result, but the types don't match. I have balanced result in two different types. So what I really mean is you have an interface, balanced result, and you have these two classes which implement that interface, right? So this is the first approximation of a sum type in Java. Basically, I've replaced and by or. That's pretty much all I've done here. Before I had transmission and generation, and that was on the input side. Now I have a delta or a violation, and it's on the output side. And the way I model that in Java is with an interface and subtypes of that. Now, where this is missing is I can't, where this is missing is being really a sum type is, if I do it this way, I can't say that these are the only two subtypes. There's actually a notion, I believe in, what is it, Project Amber maybe, of actually having sealed interfaces. It's an idea that already exists in Scala, for example, and Kotlin, where you actually can say, these are the only subtypes, tell the compiler, these are the only subtypes I have of this particular interface. We'll talk about why that's important later. The main reason it's important, I want to say balanced result is exactly a balanced delta or a limit violation, not anything else. I don't want to allow other cases because that's what I'm trying to model mathematically. And so this is where I think the programming language design from the beginning, if they had been thinking about sort of the mathematical model that they were trying to achieve, maybe would have built this in a long time ago. And again, when I do it this way, I define an interface, and if I have existing classes that I can't modify, existing classes in some library, I can't make them implement my interface. So you have to do some wrapper type. So that's where the awkwardness comes from. So what the visitor pattern, if you introduce the visitor pattern, another pattern from the gang of four, this is where you actually get a lot closer to the sum type. Because in the visitor, I could say, well, here's my balanced result visitor, and I give it a generic T to say, from every branch of this visitor, I'm going to return the same type T. And this is similar to what I had before. Remember, I had, deal with the delta. I had two methods, deal with the delta, deal with the limit violation, right? That's just an implementation of this visitor now. And what I've done with the visitor, I've said, if you implement a visitor, you only have to deal with these two cases of balanced result. So that's the way you add more structure to say this is more like an OR, okay? It's not exactly like an OR because what we're doing here is we're actually modeling functions out of the sum type as a product of functions out of the individual types. So it's a little twisted because the Java programming language doesn't have a native construct of saying I want this class or this class like it does with product. But for all intents and purposes, this is what you get. And generally you also add an accept method to the interface, which is a generic method. Okay, so when you do this, it looks like this. Balanced delta overrides accept, and this is all just extremely boilerplate. Notice the overrides of accept in the two subtypes are exactly the same. But of course, when you compile the bytecode, you're going to get different invocations of visit because the type is different there. I've overloaded visit. But the boilerplate is just the exact same code. So this visitor pattern, I think one reason it's not used very much is because a lot of times the way people model having one type or another is they put it as a product. So I have a class with field X and field Y, or result or delta and violation. And then I have two factory methods, one where the violation is null and the result isn't, and the other one where the result is null and the violation isn't. So that's typically how it's done. And then what you do is you end up with some if statements that say if is violation, cast, blah, 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 blah. So that's actually semantically equivalent. What you lose if you do that is the compiler can't check for you that you covered all cases in your if statement. When you use a visitor pattern, you implement the visitor, and if you don't cover a particular case, and later on I go and add a third case, right? I have a everything blew up case in my balance result. Then my compiler will tell me I didn't cover this case in all these particular situations. And in fact, in Project Amber, I believe, when they do the sealed types, you'll have a switch statement which will reduce a lot of this overhead of doing an anonymous interclass and whatnot. And that switch statement won't require a default because it'll know if you've covered all cases. Yes. Yeah. So the question was, the accept method has the same implementation in both cases. So couldn't you use couldn't I put make this thing a default and put the implementation here? The answer is you can't, because if you do that, the compiler will say, I don't know whether you're saying visit balance delta or a visit limit violation, because if I say visit this and I'm a balance result, I don't know which type I am. So it's a little, basically the information you get is not in the code itself, it's in the context the code is in. So the fact that this happens to be inside a balance delta means it's actually different code than this inside of a limit violation. So the meaning of this, yeah. That's right, yeah. I don't have to type it differently, but just my typing context distinguishes. Okay, so now my computation looks like this. I compute balance off of balance input, I get a balance result object. Now that balance result object is one of two different instances. If I want to continue downstream with that, I have to handle both cases because I don't know which I'm going to get. So the visitor forces me to handle both cases, and the way I do that is I say result.accept and I make a new visitor, and then I override each of the visit methods, and that override is basically back here when I first introduced it. I said consume delta, consume limit violation. I had two methods to handle the two cases, and now those two methods just look like my visitor pattern override. So you can see it's exactly the same constructions, but what you're doing here is you're letting the compiler help you. Basically, you're modeling the thing closer as a mathematical sum type, and when you do that, you get more help from the compiler. But you can also do it, with instance objects and things like that, but I think most people agree those things are not pleasant to write. Okay, so we talked about pair xy. I want to talk about either xy. Which is the dual pair. Basically, pair xy is x and y. Either xy is x or y. So now we can model, there is no either that I've found out there, like in Apache Commons or anything like that. And I think the fact that we have pair and we don't have either shows that our programming languages biases us towards products. It makes those really easy to construct. But by duality, coproducts is the official word. I didn't want to use that word. Some types are actually just as common. They're dual. Every time you dualize, you can't, basically your programming language is making you prefer one over the other. So one point I want to get across is think outside your programming language. You'll see your problems in a new light. Because if you look I can only solve this with what my programming language gives me. I mean, at the end of the day, you have to do that. But at least at the design phase, think about it in terms of just the core semantics. Simplify out everything. I have an x and a y, I have an x or a y. Those are pretty simple concepts to think about. And if you can think about that concept fundamentally, then you can say, okay, now how do I model it in my programming language? And the answer may be, actually, in some cases, it's better to model it as a class with some nulls in certain cases, but it may be better to use a visitor pattern in some other cases. But the point I really want to get across is don't let the language limit how you design a program. So the point is you can do X or Y and you can do it generically. I don't have to write a new visitor pattern every time I want to do an or of two things. So I can have an either X, Y, and then it's just a bunch of boilerplate from here, right? So now I have to do like pair is generic, so I have a get left and get right in pair. In the same way I have either a left, and it has to be still, even though the left X only has an X, it still has to be genericized on the Y because it implements either X, Y. Right X, Y, basically I have it either an X or a Y, and my two subtypes of either are left and right. Left X, right Y. Right, which means I can't just make X and Y implement either. It may not be my code to change, so I have to wrap it in a left, which I can make implement either. Basically, that's all I'm doing here. And then I have a visitor, which is the exact same thing before, except I can't just write visit, because then the compiler would get confused. So I have to say visit left, visit right. So the point is that now I have a way with this code to say, a generic way to say, here's a visitor pattern of two things, just like I have a generic way with pair. I don't have to construct a new class if I use pair. So, all right, so why is it called sum type? Exact same reason product type was called product type. You count the elements when they're finite, right? So if I have either a Boolean or a Boolean, well, I have 2 plus 2, 4. I can have just the left guy, there's 2 cases, just the right guy, there's 2 cases. With Boolean and log level, I have 2 cases for the left, 5 cases for the right. I have this or that, so it's 7 total cases, right? So, again, this is not like visitor pattern was a name made up by some programmers, but if you called it sum pattern, it actually links sort of deeper to things that existed long before programming languages. So I think there's a lot more depth when you think about the patterns in a mathematical term. Okay, so this is, again, same slide from before, except what I've done, you probably won't remember this, but I had a similar picture like this one over on the right, except all the arrows were going in the other direction. So that's the core of duality, is all I do is flip arrows around. That's all it is. It's extremely simple. Assuming you know what the arrows are. That's the really tricky part. So the point is here that now, instead of having a computation where I can, from X, compute a T and a G, right? Now I can compute an X from a balanced delta or a limit violation, a D and a V, right? So I can, from 2 different cases, I can compute the same thing. This is backwards of what I did before. From one object, I can compute 2 different objects. So this is the sense in which either is dual to the pair, or the sum is dual to the product. I basically flip the role of consumer and producer. So the point is that if I do have 2 methods, each one has the same return type, I can replace that with one method whose input is the either of those 2 inputs. Does that make sense? That's all it is. So it's the same idea where I have a construction that takes 2 types and amalgamates them into one type. One construction is called pair, the other construction is called product, or product, the other one construction is called product. The other construction is called sum. But these constructions are sort of universal in a sense. They're nothing special about Java, nothing special about any programming language that has these. In fact, what's a nice thought experiment is to think, what if Java didn't have product types, right? What if you couldn't actually write a class with members in it? That would be extremely difficult to write programs in, right? You'd have to basically insert, have interfaces that sort of continuation callbacks everywhere, right? And serialization would be difficult. There's a whole host of things which would be difficult. Imagine a programming language without sum types. You're kind of looking at Java there. but there's a way to work around it. But I believe that basically if you approach Java and you don't think about there being some types, you're missing out on a lot. Okay, so there's some more examples here. You can do the same thing with the less than or equal to. Again, I'll let you look at these if you care on the slides, but the point is that this construction is just more universal than a programming language is all I'm trying to get across here. It's actually really deep construction that you can do in many different contexts. Okay, any questions? So that ends the product and sum part of the talk, and now we're getting into what Erik Meijer actually did, or at least my version of his explanation. So questions before I move on to this part? Great. Okay, so iterable and observable are dual. And remember, when I talk about observable, it's a really simplified, basically I'm just copying what Erik Meijer did, and there's one core to it. And if you look at the Java doc, there's like 200 factory methods and combinators in that class. But basically, that one core idea is kind of, you build everything off of that. Okay, so let's start with iterable. In Java, it looks like this. An iterable is a supplier of an iterator. An iterator has a has next, a next, and a remove. Okay, so if you look at Erik Meijer's talks, he's actually working in the .NET world. They don't have a remove on their enumerable. So it makes it a little awkward to do it in Java. And, they've made remove a default no-op in Java 8. So, by JVM's own standards, I'm safe to remove. Okay, so this is a simplification, like things when they're easier. Yeah, question? Remove actually takes something out of the list. If you get a list iterator and use, though it would be the one you would get if you called next right now. Yeah, it's usually used for like a filter that mutates the list kind of thing. Iterate over it and do a dot remove, that kind of thing. But very rarely used. So, okay, so we simplified the interface to this. Next thing I want to do, and this part's a little tricky, but Erik Meijer makes the side effects a little more explicit. So I think in the enumerable interface inside .NET, there is actually an explicit exception. I'm not 100% sure on that, but basically, typically, where does the error happen in an iterable? Like, usually has next is where, say, it's a file system iterator or something. It has to actually go to the file system and see what the next file is. The next usually gives you the result that the has next found, right? So it's appropriate to put the exception on the has next. And I put the runtime exception there because it was undeclared. I'll replace it with the throwable later. So I'm just making things more explicit. That's all I'm doing right now. Okay, now what I'm doing is, notice instead of a Boolean and a T, I'm going to wrap those into an optional. So everybody knows the way you use the iterator is you're not just supposed to say next, you're supposed to say has next and then say next, right? Which is equivalent to the optional saying, hey, are you empty? If you're not, give me the element, right? So I can actually replace this, if I have any iterator of the previous kind, I can give you an iterator of this kind and vice versa, simply by giving you an empty optional when it's done and giving you a non-empty optional when it's not done. There's some, I'm not making the distinguishing between null elements because that would be where they fail. So I'd have to have some kind of value wrapper and I didn't want to go that direction. So just bear with me, non-null. So now what I'm going to do is I'm bringing this either class. So I'm going to change semantics a little bit here, but in the operational world, but not in the denotational world. So instead of throwing an exception, I'm actually going to turn that into a return type. So I'm going to think of this, basically what happens in your code, you have a try catch, and I either handle the case where I got an optional or I handle the case where I got an exception. That looks exactly like handling the output of an either. An either, I have to have a visit left and a visit right. So I handle the case visit left where I got an optional, I handle the case visit right where I got an exception. So that's where these are semantically equivalent, basically. Okay, now once I get everything into just one method with one return type, now I can dualize. And this is where I'm just flipping consumer and producer. So instead of producing an either optional throwable, I'm consuming an either optional throwable. And now this is the observer, okay, but in a weird looking form. All right, so let's restart with this thing, and I'm going to start basically unpacking what we did, and we're going to wind up at the observer that is in Rx. So the first thing is, if I consume an either, that's the same thing as consuming the left thing and consuming the right thing, right? So I can unwrap the either argument as two separate arguments. So the either is gone, but I have two methods now. Does that make sense? Fairly straightforward. Same thing with optional, actually. Consuming an optional is basically the same thing as either consuming the empty or consuming the non-empty. So I can say consume the empty is on complete, consume the non-empty is on next. Okay, so now I've unwound the observer interface, and this is exactly the observer interface that is in the Rx. So this is almost there. So we started with iterable. We got to our iterator. We constructed the observer by doing some duality. Now the observable is basically the dual of the iterator. The iterable supplies an iterator. The observable consumes an observer. All right, and this is almost it. There's one little I think the way Meijer puts it is you sort of use the denotational semantics to guide you, then you back up and you say, okay, what makes this thing more friendly, user-friendly, or what are other things we need that actually don't come from duality? You don't get everything for free from studying duality. It just sort of tells you the right questions to ask, gets you down the right path. If I have an observable and I subscribe it, I should have a way to unsubscribe it. So the actual method you get is, and this is the last slide, so is actually a subscription. I shortened the sub there, which gives you a method to say, it's like a handler registration for event listeners, that kind of thing. It's just something I can unsubscribe on. And that's pretty much it. So we basically applied some mathematical principles to dualize. Now, why would you do that? Let me just say real quickly, if you have an iterable, think about, instead of swapping producer and consumer, let's swap the side effects. So let's say the producer of my iterable has latency. Then that's going to slow down my consumer, because I'm going to say has next, and it's going to go look up in some database and assemble some things, and it's finally going to give me an answer. So I want to do some other computations, but I'm waiting on that has next. It's blocking me, right? So but on the other hand, if the consumer is slow and the producer is fast, the producer is not slowed down by the consumer if you have an iterable between them, right? So the producer supplies the next one, goes on and does its thing, and the consumer slowly computes. So if you're in that situation with a fast producer and a slow consumer, iterable is probably the thing you want. If you're in the situation with a slow producer and a fast consumer, then you've basically dualized your effects from producer to consumer. So you probably want an observable. So in the observable pattern, what you get is if the producer is really slow, basically he can call on next whenever he has something, but the consumer isn't waiting there on next. He just gave you some code that you can call. So that's where the duality comes up in practice. If you think about sort of switching some of the roles of producer and consumer in your own code. My whole point of this is I feel like it's not about understanding the abstraction, it's actually about applying it to everyday code. And in everyday code, you have problems like this. You're making trade-offs between, well, if XYZ has some latency, but ABC is fast, what's the best design to use that I don't slow one down because of the other or propagate errors correctly. So that's the kind of thing that I really want to emphasize at the end of the day. And that's all I have. You have any questions? Great. All right. Oh, we got one.
What would be a situation where the producer and the consumer weren't necessarily always faster or slower, but would depend on any particular input?
Yeah, so.
Is there a way to generalize this and switch between those patterns?
Okay, so the question was, what if you're in sort of an in-between situation? So Meijer does talk a bit about this, and there are different interfaces where, so the in-between we're talking about is like sometimes the producer is slow, sometimes the consumer is slow. If you actually look at that talk he gave, he's talking about an implementation of this observable pattern where when you subscribe, you actually give the number of things you want. So it's sort of what they call it is non-blocking back pressure, so that if the consumer starts to get slow, he can ask for fewer. If he gets fast, he can ask for more, basically. And that's where you get sort of this. You can start playing with the interfaces and where you dualize. And actually, if you look at that talk, he talks about some of that. You can start inserting futures in different places. If you have this construct of the denotational semantics in your mind, you can start tearing these interfaces apart and actually playing things like that. So I think the one that he came up that was shown, and this isn't the only one, was basically when I subscribe, I say I want the next 10 elements. And then on next will be called for those next 10. And then, once I've finished processing those, this would be the case where, let's see. I guess in this case, I'm trying to keep from overwhelming the producer of these elements. So I say or overwhelming myself, actually. I say, I'm only ready to process 10. I've got too much going on here. You keep sending them to me so fast, so I can sort of throttle the producer, but without slowing down the producer.
I would point out that OKC streams, that's like an implementation of basically that back pressure kind of thing. It's a reactive programming framework, so I've been looking at that.
Yeah, so the comment was OKC streams, which is a framework in Scala, right?
It also works in Java.
Oh, they do? Okay. And that is an implementation of a lot of these ideas that you said they use non-blocking back pressure, that kind of stuff. Yeah. Yeah. Right. Right. And the Reactor framework also, Project Reactor. Okay. Yeah. So, right. So, actually, that's so. Erik Meijer can be a little crass, so I think he like rips on this terminology of in that talk. He rips on this terminology of back pressure. He's like, I've never heard of this. They're just making stuff up, and he's just trying to be sensational, really. But the point he's trying to get across is maybe if we used more math-like terminology, which is sort of well-founded in stands the test of time, that we can make more sense of these things. But there's all kinds of intermediaries here, and the point is, once you have this duality in your pocket, you're actually free to start exploring these intermediaries. Another question?
Yeah, I was just wondering why you chose to say here that these two are dual. Like, what part of this code speaks to duality? Is it just the next and on next?
Well, basically, in the construction we did there, the duality really happened right on this slide. I flipped the input and the output. Yeah, sorry about that. Yeah, and then there's another hidden duality here in that the iterable outputs an iterator and the observable consumes an observer. So that's also duality, input and output switched. All right, I think we're good. Thank you.